All right, welcome everyone. If you're new to the world of process engineering, you're about to meet one of your most powerful tools, process simulation. So today, we're going to break down how to choose the right model for the right job to make sure your simulations actually match what's happening out there in the real world.
Look, we've all been there, right? You spend hours building this perfect simulation, this beautiful digital twin of your plant, and then you run it and the numbers are just off. They don't line up with what the operators are seeing on the screen. It's a super common problem, and the answer, believe it or not, usually comes down to the fundamental choices you make before you even draw the first piece of equipment.
To really wrap your head around this, I want you to use a simple analogy. Just ask yourself, are you trying to take a perfect photograph of your process, or are you trying to film a movie of it in action? Seriously, that one question is at the heart of everything we do here.
So let's really break this down. On one side, you've got your steady-state simulation. That's our photograph. It's a perfect snapshot in time. It solves a single mass and energy balance for a process that's just humming along in a stable, equilibrium state. Time isn't a factor. But then you have the movie, the dynamic simulation. This is totally different. It builds on the snapshot, but it adds the crucial element of time dependence, solving those balances over and over again as things change.
Okay, so let's talk about that photograph first. I want you to think of a steady-state simulation as the essential blueprint, the foundational document you create when you're first designing a plant or a new piece of equipment.
This is your bread and butter for design work. You use these snapshot calculations to answer all the big, critical questions up front. You know, what temperature and pressure do we need to make our product? How big does that heat exchanger have to be? Is there a smarter way to lay this out to maximize our energy recovery? It's all about design and optimization when you assume everything is running nice and smooth.
Right, but what about when things aren't running so smoothly? What happens when things go sideways? For that, you need the movie. You need a dynamic simulation, which is basically a stress test for your entire plant design.
And this is where it gets really important. Any process that unfolds over time absolutely demands a dynamic model. We're talking about the incredible complexities of a plant startup or a shutdown sequence, or even more critically, what actually happens during a pressure relief event or a sudden unexpected utility failure. These are the moments where a simple snapshot is completely blind to what's going on.
Let's just take an emergency depressurization as an example. A steady-state model tells you nothing about the critical moments, like the liquid level swelling up inside a vessel, or the rapid flashing of liquid into vapor that could totally overwhelm your relief system. A dynamic model lets you see that whole event second by second. That data isn't just nice to have, it is absolutely vital for designing a safe system and for correctly calculating things like latent heat when you're sizing a safety valve.
Okay, so you've made the big choice, picture or a movie, but that's only half the battle. Now you have to pick the right engine to actually run the simulation. And in our world, that engine is the thermodynamic model, or what we call the property package. So what is a property package? Well, it's a whole collection of specialized mathematical models that calculate how all the different chemicals in your system are going to behave, how they interact when they become a liquid or a gas, all of it. Let me be clear, getting this part wrong is probably one of the top reasons the simulation fails to match reality. It's truly the brains of the entire operation.
So let's look at a couple of the most common models, especially for hydrocarbon systems. First, you've got Pang-Robinson, or PR. This is the industry workhorse, for sure. It's incredibly reliable across a massive range of temperatures and pressures. Now you can compare that to SRK, and while SRK can give you similar results in some cases, its effective operational range is just much more limited. That's exactly why for most oil, gas, and petrochemical systems, Pang-Robinson is going to be your go-to.
But what if you're not just dealing with simple hydrocarbons? What happens if your system has things like alcohols or organic acids? These chemicals are what we call highly non-ideal. Their molecules have these strong polar attractions that an equation of state like Pang-Robinson, which was designed for non-polar stuff, just can't capture accurately. So to model these complex interactions, you must switch to a completely different tool called an activity model if you want to get results you can trust.
And you know, even within the world of hydrocarbons, that specialization still matters. If you're working with heavy hydrocarbons, a model like Chow-Cedar is often your best bet. But for systems dominated by light gases, you'd be much better off using the Benedict-Webb-Rubin equation. The key takeaway here is simple. Always match the tool to the specific chemical system you're trying to model. So, with all that in mind, how do you actually put this all together in practice? Well, here's a clear step-by-step checklist that you should be following every single time you build a simulation. Okay, so here are the standard 6 steps. First, you select your components. Second, you pick that all-important property package. Third, you build your flow sheet. Fourth, you specify all your known streams and compositions. Fifth, you run the simulation. And sixth, you interpret the results. But I'm adding a 7th non-negotiable step here, and it's the most important one. Validate your plant data first. Remember, the simulator is just a calculator. If the plant data you're feeding it isn't consistent or accurate, your results will be completely meaningless. It's the classic case of garbage in, garbage out.
All right, let's bring all this theory back down to what really matters on the plant floor: safety, reliability, and making sure our operators are ready to handle anything that gets thrown their way.
So why does getting this modeling fidelity right actually matter? Well, think about it like this. For sizing a pump or a tank, standard equipment, a steady-state model is usually perfectly fine. But for sizing the control valve that actually operates that pump, you absolutely need a dynamic model. You have to understand how that valve is going to respond over time to changes in the process. It's a perfect example of needing the right tool for the specific job.
And this is where dynamic models are just invaluable. They are, for all intents and purposes, flight simulators for our plant operators. You can use them to train operators on exactly how to handle a sudden cooling water failure or to practice an emergency shutdown procedure, all in a completely safe virtual environment. It builds the muscle memory they need to respond correctly and instantly when a real crisis hits. So as we close this out, I want to leave you with one final thought to chew on. We've talked about these models as tools for design and training, but as our plants get smarter and more automated, think about the future. How will running these incredibly complex digital stress tests in real time completely redefine how we think about and how we ensure the safety of our facilities? That's the challenge for all of us going forward.
Thank you. If you want to learn new skills online, join our expert lead training courses. Visit our website, www.ohmsolglobal.com, or send your queries at admin@ohmsolglobal.com. For more videos, you can follow our YouTube channel.